All right, so from notes from Thursday or Wednesday, we derive this expression that at equilibrium that the delta G of a reaction is minus RT times the natural logarithm of the equilibrium constant. Okay, so what we want to do is we want to calculate a difference in delta G. How much does delta G have to change such that this K changes by a factor of 10? All right, so let's think about that. So what we want to calculate is, say, the difference in delta G, which is the difference of the delta G of reaction G prime, which gives us the speed, right? That's what we want to solve. We want to, for our new delta G, minus the original delta G. And that's going to be equal to minus RT ln K prime minus RT ln K. Okay. So we want to calculate this difference. This is delta G. We want to calculate this difference such that K prime over K is 10. Right? Make it 10 times more product favored. All right? And so that means that, let's just do a little bit of math. That means that delta G is going to be equal to minus RT, we get rid of the minus sign, no, yeah, minus sign's there, times the ratio of the product of the equilibrium constants, right? Right, and what's the ratio? It's 10. So this is going to be equal to minus RT log 10. Okay. So what this means is that we have to change, in order to get a factor of 10 improvement, we need to change delta G by this difference. But that's temperature dependent. Okay, so it's temperature dependent, right? Because entropy plays a role, and that's going to be a temp in delta G. So it's going to be proportional to T, right? But it's always fixed by this ln 10, right? No matter what temperature you're at, you're always going to have a logarithm of 10 on the outside, right? So the amount of energy that you need to increase the equilibrium constant by a factor of 10 is always RT log 10. Okay, so let's just calculate that. Let's do it at 300 Kelvin, right? Just the normal temperature. 8.3145 joules per mole per Kelvin. Times 300 Kelvin. Times the logarithm of 10, which I'll just give it to you right now. Should be about 2.3 if I remember correctly. Yep, it is. 2.302. That's a really easy calculation for us to do. 8.3145 times 300 times 2.032. Just kind of stick it here on the side. And this is 5.74 kilojoules per mole. Okay. And he gave a value of something like 1 something in kcals. And a kcal is 4.184 joules. So we need to divide this by 4.184. This is 1.4 kcals per mole. So keep that in mind in the future, that to get a factor of 10 change in equilibrium at room temperature, we only need to jiggle the energy by a small amount, by 5 or 6 kilojoules per mole. So that's why he said it was about 1.4, because that's exactly what this comes out to. Right? So this is kind of an important, kind of a subtle point. Is that the relationship between moles, if you will, right, quantities, the stuff that we pull out of our system, is exponential in the energy. Energy changes in energy lead to exponential changes or logarithmic changes, if you will, in K. Right? And the amount of material that you get from one side, products versus reactants, that's a very, 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 very sensitive function. It's exponential in the energy difference, or the delta G. Right? So small changes in delta G can lead to very, very large changes in your reaction conditions and your reaction products because they're related to each other exponentially. Right? This is one of those kind of things that you don't really appreciate in chemistry, that this is not a linear relationship, and that if you double the stability of a material, it doesn't give you double the material, it gives you a lot more than double the material, right? Because it goes as the log. It gives you a lot more. So energy and material is a logarithmic scale, not a linear scale. So small changes in energy lead to large changes in mole number. Any questions about that? It's a good answer. Good question here you asked. And it's good to think about, you know, things like this. It's just really kind of good, these are one of these like rules of thumb that we have in chemistry. You know, factors of 10, when you're talking about abundances or kinetics or relative intensities or equilibrium constants, factors of 10 in those at room temperature tend to be associated with changes on the order of about about 5 kilojoules per mole. That's kind of that typical relationship you get because of this logarithm right here. Right? For the t, this is always fixed, and log of 10 is always the same number. So this number shows up a lot in chemistry. Factors of 10 tend to be on the order of 6 kilojoules per mole. We'll see that in kinetics as well. We talk about how to make a reaction 10 times faster. This kind of calculation will appear again. If we want to catalyze something, we'll think about that as well. Okay. So I want to talk about one more conceptual thing before we do a problem. I want to continue on with equilibrium. I think the best way to do equilibrium is with problems. I want to talk about this equation that I derived in class that I think was a little confusing. But it's this idea. So let's imagine now, let's go back to our, sorry, let me undo all this. I'm trying to draw a coordinate system. So let's imagine again that we have A equilibrating with B. All right, let's just do a one-body problem. Right, and this system is a function at fixed temperature and fixed pressure as a function of two variables, the Gibbs energy. Right, the Gibbs energy is going to be a function of the chemical potential, or sorry, not the chemical potential, rather, the number of moles of A and the number of moles of B. And we can plot that here. Right, so we have some surface, some energy surface that's a function of A and B. I didn't want that like that. Let's do it like this instead. It's a really bad function, but you get the idea. So we have this surface here. Well, it's like a surface where we have this minimum energy point here. Right? This is so we have delta G is equal to 0 here. This is the equilibrium point. And the idea is that we can pick any point along this curve. Let's pick this point, G of A1, B1. And we can always write that delta G, this is delta G, sorry, let me write this as delta G. Delta G at this point is equal to the delta G of reaction at room temperature plus RT ln Q, where Q here is just the equilibrium constant, which is the partial pressure of A over the partial pressure of B, or vice versa. Right? This is the equilibrium constant, or the reaction coefficient. Right? Remember, G wants to be as negative as possible. Right? So if we're up here, at this point way up here, we know that the system is going to remove A. Let's say that this is increasing A, and this route is increasing B. Right? The system is going to remove A in order to reach this minimum point, right? The equilibrium point. So if we think about the Q at this point, right? We want, right? So at this point, we have delta G, right? So the energy of this point right here is delta G of reaction. The equilibrium point is at that energy. So we here at this point at delta G of A1, B1, this is greater than delta G of reaction, right? We're at higher energy, right? And that, of course, means that RT ln Q is greater than 0. Right? And so that means that Q is too large. Do I get this right? Do I have a negative? I think I have a negative sign wrong. Do I have a negative sign wrong? Hold on, let me just check really quickly. I might have missed a negative sign here. Ah, here we go. Sorry about that. No, that's right. Oh, I know what's wrong here. So Q is too large. Right, so we want to deplete A and make more B. Yeah, actually, so this is the wrong sign. Go ahead. You're probably asking about the same thing I'm realizing at this moment. So one of the issues here is that what Monica's going to say is that as you add A, Q gets bigger, or Q gets smaller. But right? No, that's what we want. Sorry, we want to remove A.
Don't you want to add A? You want. Well, if your Q is too big, you want
right.
Q to get smaller.
Right, so you want Q to get, right, so actually the way that I've done this is actually this needs to be lower energy, it needs to be negative instead.
Okay.
Yeah, so let me fix that really quickly. So let me erase this. So let's do that instead. So imagine now again, well, I'll draw this in a different way to kind of simplify it for you guys in a second. I just want to do it graphically, right? So let's let this go down instead. And this is increasing A. Right, so here's our point here, G of A1, B1. G of A1, B1. G of A1, B1 is less than the reaction. Oh, sorry, it's greater. Oh, wait, hold on. I screwed this up. All right, guys. Let's start over. I'm sorry. Let's do a problem, and I think it'll become more clear. I'm confusing myself now. Let's do a problem to illustrate this idea. So let me first schematically do this. Okay, so again, let's look at A. I'm going to do this a different way. I apologize, guys. I think it'll become more clear what's going on in a second. So let's have A to B, okay? So let's think about the energies of A and B by themselves. All right, so let's say, for instance, let's just say that this is a reaction, delta G of reaction is less than 0. Okay, so it's going to go downhill in energy. All right, so if I make a plot here, of, let's say, the energy of A. So this is delta G of formation of A. And this is delta G formation of B. Okay, and this is a plot of delta G. All right, so the idea is that the energy of A, the free energy of A is higher than it is of B. All right, so this energy difference in purple corresponds to the reaction energy at equilibrium. Okay, and we have that at equilibrium. Delta G of reaction is minus RT ln K. Right? And remember that K here we can write, for instance, as the concentration or the number of A divided by the number of B, if you will. Right? And what does this say? We can take e to the both sides. It says that B over A is equal to e to the minus delta G over RT. Delta G reaction of RT. Right, again, this is where that exponential dependence comes from. Small changes in G lead to exponential changes in the ratio of products versus reactants. Okay, so if we just let this system equilibrate, we put A and B together. We put A and B together and we let the system sit for a little while. Will it update? It's frozen again. I bet you my Zoom is about to crash again. And it crashed. Go figure. All right. Reconnecting. Okay. So anyway, so at this energy difference that you can see here, I wanted to scroll the screen over a little bit here. We can predict, if we can measure those Gibbs energies of formation of our reactants and our products, we can find exactly what our equilibrium constant is, right? Our ratio of products versus reactants. So I'm still connecting over here. Oh, it's just not been my day today.
It makes sense what you're saying.
Yeah. All right, here we go. Sorry, friends on Zoom. I apologize. Okay, much better. Right. This energy difference tells us something about it, okay? But let's imagine now that we're not at equilibrium. Right? We don't have, let's say we start with just A, right? Right? What if we're at the beginning of the reaction? Let's just say N of A is 1 mole and NB is 0 mole. Okay, so now what are the energy differences of the initial versus the final in this box with these initial conditions at the initial point? Right, we've got all this A and none of this B, right? So what the energies of each of the initial and the final states, the products and reactants, are going to change by that amount. Right? So this energy, for instance, for A is going to increase by some amount, which is equal to the chemical potential of A times the number of moles of A. And NB, of course, is 0 moles, so this is 0 at initial conditions. Right, so delta G of B at initial conditions is 0, and delta G of A is equal to the free the energy of formation of A plus mu A in A. Okay, so what's happened is now we've taken the energy of the box, right? These are the regular energy differences between A and B at equilibrium. but I've driven my box out of equilibrium, so I just have A, right? So the A part of the box rises in energy with respect to the chemical potential of A by that amount. And the free energy of the box where B is, and again, think about this not as a reaction, but as two compartments. One that has A that's moving into, and the A molecules move into the B box, so now B, when B moves in A, they're A. So think about free motion of molecules across a membrane in a box. So we have tons of energy in the A box and no energy in the B box because there's no molecules in it, right? N is 0 initially. Right, so our Gibbs free energy difference initially is the difference between GA and GB. Right, so initially, the total Gibbs energy of the system is GA plus GB, which is the Gibbs free energy of A plus mu A in A. Right? And that's, of course, as we can see from here, right, that energy difference is much greater than the reaction Gibbs free energy. Right? Because the reaction free Gibbs energy is the difference between here and here. Right? That's the difference between the two boxes at equilibrium. And this is what we have initially, is this big difference. Okay, so what is the system going to want to do? Well, it's going to want to, right, lower the amount of A molecules and correspondingly increase the number of B molecules, right? Because the B molecules have lower energy on average than the A molecules, right? So for every one of these that I lose here, let's say I lose a mu A here, I'm going to gain some mu B, equivalent, a stoichiometric amount of mu B, of B molecules, but the amount of energy that it increases is less because they're more stable. Right? This is the amount, if you think about it, delta G of formation of B is the delta G of 1 mole of B molecule. Right? So if I bring this system down, like if I let the system react a little bit, to this point in purple, right, the energy of this will be mu A Na minus the number of clicks, the extent of the reaction. And then here I would have mu B in clicks, right? Because for every molecule of A I lose, I gain B. Or I gain 1 in B, in clicks in B. Right, so as the reaction starts to equilibrate, right, I'm starting to lose molecules of A and forming molecules of B. And the amount of energy that each molecule of B adds to the B box is mu B. And each energy that as we move A molecules, each amount of energy that the molecule of A, the box A loses as the molecule of A becomes B is mu A. Right? So as I lose some amount of molecules of A, the energy goes down proportionally to mu A, and then the energy on the B side of the box rises proportionally to mu B. But if delta G of reaction is less than 0, this means that the Gibbs energy of A is greater than the Gibbs energy of B, which means that the chemical potentials of A is greater than the chemical potential of B. So the idea is that if this is true, the stabilization provided by the loss of n bar particles of A, right? That's the stabilization, I mean, is energy decrease. So this energy decrease in magnitude is greater than the destabilization, or the energy increase, by the addition of n particles B. Right? The stoichiometry says every time I lose a particle of A, I have to gain a particle of B. Right? So every time I lose a particle of A, I lose mu A energy, and I gain mu B back by making B. But mu B is less than mu A because B is more stable than A. So what happens as the system equilibrates is the system loses energy in the A box and gains it in material equivalents in the B box, but some energy is lost because each molecule of B brings less energy to the table than each molecule of A. These are more stable. All right, so what happens is that the A gets depleted very, very rapidly as the B starts to rise up. Right, so eventually I let this system equilibrate, and what happens? Well, the system is going to decrease, right? The amount of A is going to decrease until it hits here, the Gibbs free energy of A, and the energy of the B box is going to increase the same amount to here. Right? And then eventually the system reaches equilibrium, right? Because at this energy difference, here and here, the chemical potentials has changed between A and B such that every molecule of A that I add at equilibrium is compensated by a loss in B and vice versa. Right? So the system eventually equilibrates, and when it hits this point where the A is at this energy and the B is at this energy, the chemical potentials end up being equivalent to each other. Right? Because remember, the chemical equivalents are changing. I'll write that over in the corner. Right? Remember that the chemical potential at some pressure is the standard chemical potential plus RT times the log of the pressure of that material divided by the standard pressure. So as the number of particles of B increases, the chemical potential of B is increasing because P is increasing. Right? So mu B is increasing with value as B increases. So the amount of energy each B molecule brings to the table gets larger and larger as B increases. And likewise, the opposite happens in A. A gets depleted. Its chemical potential drops because the pressure of A is decreasing as well. And so each molecule of A brings less and less to the table as you have less and less A molecules. And eventually, you get to the point where the amount of energy a molecule of B brings to the table, like maybe from right here, and I add a little bit to right here, that's equal and opposite to the same amount of change in A with its chemical potential. Because at equilibrium, the chemical potentials are exactly the same. Right? What that means is that at this energy difference here, Gibbs energy of reaction, the one in orange, the equilibrium energy difference, these total chemical potentials with the P's, changing with the P's, you add that for A and you add that for B, they're equal to each other. So at this equilibrium point, the chemical potentials of A and B are identical after this correction here. So what happens is that as I add A by some amount, B will decrease by the same amount. And if I add B, A will decrease by the same amount as B increases. So at equilibrium, what this says is that I'll just do this in lime green, is that any change in dB is compensated equally by a change in Na at equilibrium. Okay. So there are kind of two Gibbs energies we're tracking. Right? There's the Gibbs energy between the products and the reactants. Excuse me, sorry. the products and the reactants. So there's this Gibbs energy that we're measuring for the difference between the box A and box B, or products and reactants. That's a function of time. right? It's a function of the number of molecules, right? So we have a Gibbs energy that tracks, again, you can measure Gibbs energy at any point. The Gibbs energy is defined at every point in A and NB, doesn't matter what they are. But if NA and NB aren't at their equilibrium positions, then that means that either the energy of B is too low or the energy of the A box is too high or vice versa, and the energies need to re-equilibrate. Okay, so there's going to be a delta G that you measure at any point. And if that delta G matches exactly the delta G that you get for equilibrium, then you're at equilibrium. So what I can say now, so the idea now is that if delta G at any point in reaction is not equal to delta G of reaction, then system is not at equilibrium. But if delta G is equal to delta reaction of G, system is at equilibrium. Right? Because we have delta G is equal to delta reaction of G plus RT ln Q. And this Q term, this is defined for all points where the chemical potential of A may not be the same as the chemical potential of B, but if we're at a point delta A is equal to delta B, or mu A is equal to mu B, this means that delta G minus delta reaction of G is 0, and therefore delta reaction of G is now equilibrium. The G we're measuring is the equilibrium one, and we get delta RT ln K. All right, so Q, if you will, is an equilibrium constant defined for any point in the reaction. Right? So the value of Q will tell us where we are in the equilibrium. Right? If Q is larger or smaller than what K should be at delta G, then we know we're not quite to the finish line, or we're past the finish line. We need to go backwards. We've created too many products, for instance. Right? So Q can tell us that. All right, let's do an example. Any questions? All right, this is a fun example. Fun is a relative word, I guess. All right, so let's look at a reaction that I'm somewhat familiar with, I've worked with over the years, and it's one of those that you just have to deal with when you work with nitrogens. It's the reaction of N2O4 with 2 molecules of NO2. Okay, so if you buy you can buy either of these gases, and theoretically you can make them too, and they always come up as a mixture. So I have an experiment from like 2013 where I worked on NO2, and I got this container of NO2 from someone else's lab, this ancient spectroscopist whose credit to fame is he's published a paper on on molecules how to say this. Lester Andrews is so old that he's published a paper on a molecule that contains at least one of every naturally stable isolable element in the world. Right? So all the way down to uranium he's studied. And he gave me this thing at NO2, and I put it in my spectrometer, and there's all sorts of crap, just tons of junk. And then I realized the reason why is because you get N2O4 and other types of oxides as well. So these oxides in the gas phase exchange a lot. NO2 gas is really nasty, toxic. It's this brown gas. It's what causes smog to be brown, for instance, nitrogen oxides. NO2 is the classic brown nitric oxide that causes that kind of gross-looking brown smog that you see in cities. Okay, so I want to look at the equilibrium of this reaction. Okay, so let's again define our setup. So first we'll let T be 298.15 Kelvin. We'll come back to pressure in a second. Okay, so let's start by just having a little bit of N2O4. Okay, so our initial conditions, we're going to have 1 mole of N2O4 and no moles of NO2. Okay, and now we're going to let the system equilibrate. Right, so during equilibrium, every time the reaction clicks, you could say that N2O4 is 1, and every time it clicks, it loses 1 molecule, right? Because it's a 1-to-2 relationship. So we lose, for every click in, we lose 1 mole equivalent. And then for NO2, every time it clicks, we gain 2. So how can we write the Gibbs energy of this system? Right, so I want to write the Gibbs energy as a function of our variable, which is n, our little n tilde, our extent of reaction. Right, and what's that going to be? Well, it's going to be the moles of N2O4 times the Gibbs energy of formation of N2O4 plus the Gibbs energy of NO2 times, the Gibbs energy of formation of NO2 times the number of moles. Okay? So as a function of n, this looks like 1 minus n tilde in squiggle times delta g f of g in 204 plus 2n squiggle delta g delta f g of NO2. Okay, so what I want to do now is I want to convert. We can't really measure the metronome, right? That's happening very, very rapidly. So we need to track it with something that we can measure. So let's, again, like we did in Wednesday, convert these to partial pressures, right? We can measure the pressures of the gases. So let's instead relate these now to partial pressures. Right? And we can use that formula that relates to Gibbs energy of a system. So the Gibbs energy of N2O4. Or this is the Gibbs energy of formation. Sorry. Gibbs energy of N2O4 is going to be equal to the Gibbs energy of formation of N2O4 plus RT times the log of its pressure divided by our standard pressure. And we can write that for NO2 as well. Let me clean this up a little bit. These are just regular Gibbs energies. I apologize, but that's okay. It doesn't matter. The work is exactly the same. All right, so I can plug these now into my expression. So I have the Gibbs energy of the system at any point along the reaction n is going to be 1 minus n squiggle times the Gibbs energy of formation of N2O4 plus 2 n squiggle times the Gibbs energy of formation of NO2 plus 1 minus n squiggle RT ln P N2O4 P naught plus 2n RT ln P NO2 over P naught. Okay, So we have two variables here. We have pressure and N. So I want to convert one into the other. All right, so what we need to do now is we need to convert N to partial pressures. Okay, and the partial pressure of a material is its mole fraction times the total pressure. Right, that's the mole fraction. So for N2O4, the mole fraction is going to be the pressure of N2O4, or the mole fraction, sorry. It's going to be the number of moles of N2O4 divided by the total number of moles in the system times P total, which is 1 minus N tilde divided by the sum of the moles, which is 1 minus N tilde plus 2N, which is 1 minus N tilde over 1 plus N tilde. Oh, we'll do it in terms of N tilde, P total. Okay, so that's for N2O4 and NO2. It's the same idea. We have 2N over 1 plus N times P total. All right, so I'm going to do everything in terms of N, not pressures. We could swap around if we wanted. I think it's easier to do in terms of N. I was just confused. So we now have expressions for the partial pressure of N2O4 and the partial pressure of NO2 that we can plug into our logarithms. So now we have the G of N factorial is equal to 1 minus N squiggle times the delta G of formation of N2O4 plus 2N squiggle G of formation of NO2. And then we have these logarithms plus 1 minus N squiggle times RT times the log of 1 minus N over 1 plus N P total over P naught. And then we have 2N times RT ln of 2N over 1 plus N P total over P factorial, or P naught, standard. All right, so we've got this equation here that's a function of N, which again is the extent of our reactions. Remember, N just tracks how many moles have been created. Right, this is 1/2 the number of moles of B, right, because you form 2 moles of N every time. All right, so this tracks how much B is formed, if you will. Okay, and so in order to find equilibrium, right, what do we need? We need to minimize G, right? We need to find dG with respect to N and set it equal to 0 to find minimum. Right? And so we can certainly just take a derivative of this function if we want. But let's just do it. Let's do it graphically and numerically instead, right? So let's just kind of work this problem out.
Can I ask a question?
Yes, please.
Why are you doing like the dg over dn equals 0? Because like isn't
Well, Gibbs energy, remember, is the energy of the flask, if you will, as a function of the reaction extent. Right? So when n is 0, the reaction started. And then there's going to be there's an n where you've converted all your A into B, right? And so n can go from 0 to 1. right? Because N is equal to 0, you have 1 mole of your reactants. N is equal to 1, you have 0 moles of your reactants, right? So N can be anything between 0 and 1. And this tells us the Gibbs energy of the system for any value of N between 0 and 1. And where does equilibrium happen? It happens where where the Gibbs energy is minimum. Remember, when energy is minimum, we always want to find energy minimum. Right? That's the principle. That's the energy minimum principle, right? Right? Equilibrium occurs. Where does equilibrium occur? In any thermal equilibrium, right? It occurs where the derivative of the energy with respect to the coordinate is equal to 0. And the second derivative of the energy with respect to the coordinate is greater than 0, right? This is a minimum. Right? It's a minimum. So we need to find, right? So now we have a function g of our variable n. And so in order to find where equilibrium occurs, we have to find where g gets minimized, right? Does that make sense?
Yeah.
Okay. All right, good. Right? We always apply these two constraints when we want to find equilibrium. We find the minimum energy. Right, so instead of doing that, we can certainly take a derivative and solve for 0, right? Not a big deal. But we have some things that we can solve here, right? We can work out, right? Maybe we can calculate the Gibbs free energy of N2O4, right? We've got some things that maybe we can calculate from literature to simplify this problem. So let's define a few things. So first, let's set P total, right? The total system to be 1 bar. The standard pressure to be 1 bar, right? So that the P's go away. And again, we're setting T to be 298.15 Kelvin. Right. So let's go look for, so the only two numbers that we need to know now are the Gibbs free energy of NO2 and N2O4. Okay, so let's go look them up. Let's go to NIST. Type in NO2. Nitrogen dioxide, gas phase thermochemistry data. And there we go. There's our HF and our S. All right, so our enthalpy of formation is 33 kilojoules per mole. Sorry. And our entropy of gas, our delta F of entropy, is 240 joules per mole. So that's 0.24 kilojoules mole Kelvin. And then for N2O, N24, for dinitrogen tetroxide, nitrogen tetroxide, we have the enthalpy of formation is 9 kilojoules per mole. And delta F's of formation of entropy is a little higher, 0.304 kilojoules per mole per Kelvin. Right, and we of course can calculate delta G of formation as delta F H minus T times the enthalpy of formation times the entropy of formation at that temperature. And what we get, again, not too hard for you to do these numbers, NO2 is equal to 51.253 kilojoules per mole. And delta F G N2O4 is 97.787 kilojoules per mole. Okay, so which way did we do this reaction again? N2O4, right? So we have a product. If you look at it, it looks like it's more unstable than NO2, right? By 40 kilojoules per mole. Right? It's 40 kilojoules more Gibbs energy than NO2, right? NO2 is a product. But what if we forgot? We forgot the stoichiometric coefficient, right? So for every one of these, 97, we get 2 of these. So what we really should compare is this number to 2 times this, right? So this says that the product, the reactants are 98 kilojoules per mole, and the products are 102. Right? So actually, this reaction is reactant favored, right? Because really what we should look at rather is that this is equal to 2 mole is equal to 102.5 kilojoules per mole. Right? So that means that delta G of reaction for this system is the difference between 102 and 97. And we'll say that's roughly 4.5 kilojoules per mole. All right, so this should be reactant favored. Right, because it's favored towards the reactants have lower energy than 2 mole equivalents of the product. All right, so I can plug in all these numbers and then just go into Excel and calculate my curve. And this is what it looks like. Oops, that's a terrible. So I'm going to plot on the x-axis the reaction extent, which of course has units of moles. And I'm going to plot delta G of the reaction at any point as a function of n. All right, and n can run from 0 to 1 because there's 1 mole of reactants, and this tracks the loss of reactants. So 0 and 1 are our 2 options here. All right, so we can figure out immediately where the intercepts of this equation are. Because this intercept n equals 1 is all B, and this intercept equals 0 is all A. All right, so at G equals 0, at n equals 0, the Gibbs free energy of the system is just the energy of the products, or the reactants, right? So that's going to be 97.787. Right, so I'll put 100 here. 90. Actually, that's too coarse. Sorry. 98, 102, 96, 94. Okay. All right, so the reactants, when we have all just reactants, right, the Gibbs energy of the system is just the Gibbs energy of A, which is 97.787, right? So it starts about right here. And then when we have all B, our Gibbs energy of our system is 2 times the Gibbs energy of NO2. So that's 102.5. That's going to be up here. Right? And we know Gibbs energy should be a smooth curve, right? So we have some curve that's connecting these 2 points right here. Right? So it could go like this, but we know that it's not going to go like that, right? It has to have a minimum, right? There should be some equilibrium point. So this energy should have to go down, and there should be some minimum in the middle where the sign changes and it continues upwards, right? This should equilibrate somewhere. Okay, so this thing should start to go down 0, and in fact, that's what you see. Right, and we can even predict exactly if the delta G of reaction is 4.5 kilojoules per mole relative to 97.787, then that means the equilibrium point is going to be somewhere around in the 96 to 95 region. So when you plot this curve, it gives you this nice, smooth, almost parabolic-like thing, like this. And so again, if we start at this point at n equals 0, right? Think about it like a ball. What's the ball going to do? Well, it's going to roll down the hill, right? To get to a lower point on the hill. Right? So that means that we're losing A here, or losing N2O4 here. Right? But if we catch the equilibrium way over here, the ball is going to roll this way. This is losing NO2. Right? And eventually there's going to be a place where those balls meet, right? And those two balls are going to meet right here. And this is the equilibrium point. It's actually a little, I've screwed my scale up a little bit, but I'll make this 0.2 just to cheat. Right? So this is our N, this point right here is NEQ. Right? And this is where the Gibbs energy derivative is equal to 0, right? It's at the minimum. Right? So this is what we're tracking with Gibbs energy. We're tracking the energy of the box, or the two-compartment box, the A's and the B's. They're exchanging back and forth. And if you got too much A or you got too much B, the energy is too high for your system, right? And so the energy is going to decrease. Right? So the system is going to exchange, in this case, B into A, or A into B to lower the energy. And eventually there's a point where adding A or removing A is the same as adding B or removing B, right? In some ways, the idea is that the energy, when you're at this point, the energy increase in this direction is the same as this direction. Right? So it doesn't matter which way you go. Right? There's no preference that every force in this direction is compensated by an equal and opposite force in the opposite direction. Right? So this system equilibrates right to this point here. And I've unfortunately drawn my scale very, very poorly. In fact, I'm going to cheat a little bit here. I'll call this 1.1, 0.5. Is that when you calculate this, so that you find that the minimum point is 0.1892. Okay. And so what does that tell us? Well, that tells us that this tells us exactly how many moles of N2O4 we've lost and how many moles of NO2 we've gained, right? This is going to be half the amount of moles of NO2 we've gained, right? So this says that at 298 Kelvin, that when you put N2O4 in a box and you let it equilibrate, that you lose effectively 18% of your material and you form mole fraction 36% NO2.
Can I ask a question?
Yes.
Could you show which equation you used to calculate the N, the 0.1? It's
Yeah,
just that
it's literally this equation. I plug in the numbers, set it, and then take a derivative and set it equal to 0. Yeah, just solve it for 0. But another way you can do this, and this is actually, I think, the way that I end up calculating this number is, you can solve it algebraically, but another thing is that you could, right, just calculate this curve yourself and then pinpoint exactly on the curve where that minimum point is, numerically.
So, like, why would you, like, I guess fun versions, like, why would you do this instead of just doing, like, what you do in, like, quant, where you, like, just
Where you
solve,
do ice?
like, yeah.
Good question. Why is it? Well, first of all, that's a good question. So first of all, that's correct. But the reason why I do it this way is to show you exactly what's going on, right? So when you do it with ice, you're assuming that the system, that you started somewhere, and you're going to end up at this point, right? But you don't really know what that curve, what the Gibbs energy does. I'm just trying to show it to you in specific details.
So
Right.
Okay.
Now, ice, you're right. You'll get the same result from ice, right? Doing an ice chart, if you know all this data. But here, I just want to show you from the ground, right? You're making a lot of assumptions using ice, right? By doing it in CHEM. We'll come back to that idea, actually, next class. But I just want to show you technically what's going on in equilibrium, right? What's happening actually is that the systems, you've put the system at a very high energy, some high energy, and the system needs to change the number of molecules that it has, boxes from the A compartment to the B compartment or vice versa, in order to find a minimum in the energy function, and that minimum in the energy function corresponds to where it equilibrates. There is a weakness to ice. All right, so let's look at ice. Let's think about ice for a second, right? So in this reaction, what is Kp, the equilibrium constant? All right, well, Kp is the partial pressure of the products divided by the standard pressure squared. How much time do I got left? Good. Divided by the partial pressure of N2O4, divided by the partial pressure. All right. Well, we have formulas for these. We wrote them down when calculating mole fractions. This is 2n factorial divided by 1 plus n factorial times P total over P naught squared over 1 minus n factorial, or sorry, n factorial, n squiggle times P total over P. All right, and P total is just the total pressure of the system. Okay. All right, so let's just simplify this a little bit. This is 2n. We have a 1 plus n. They cancel out. We get a factor of P total cancels out here. We get 2n squared. We get 2n squared over 1 minus n. Oh, wait, sorry, that's not right. We have a factor of 1 minus n, so we have, sorry, only one factor of 1 minus n gets 1 plus n gets canceled out. So this is 2n over 1 plus n. Let me clean this up. Okay, so we have a 1 minus n times 1 over P naught here in the denominator. And then we have a 2n squared over 1 plus n, that's the remaining one, times P total over P naught. P naughts cancel out, and we're left with 4n squared divided by 1 plus n factor, 1 plus n, 1 minus n, P total, right, which is equal to 4n squared over 1 minus n squared times P total. Right, so we could plug in, right, so at this is actually Q. I should say that this is Q. It's only Kp at equilibrium. Right, so at equilibrium, right, remember that n factorial, or n, I keep calling it factorial, I'm sorry, but the equilibrium n is 0.189. And so this means that KEQ is 4 times 0.189 squared over 1 minus 0.189 times P total, which is 0.148 P total. Now, the thing that I want to point out here, if I set, right, I originally set the problem P total to 1 bar, right? So we're at 1 bar, right? So this system is very clearly product favored or reactant favored, right? But what happens as I increase P total? Right, what happens as I increase P total? Well, so as I increase P total, right? So at KEQ, let's look at this right here. KEQ is fixed. Right? Remember, KEQ is fixed by delta G. Right? So if we're at 298, and we're assuming delta G doesn't change with pressure, which is true, delta G of reaction doesn't change with pressure, this number is fixed to whatever it is at that temperature. Okay? So we have a fixed number here. Right? That's a product of a number that's changing times another number that's changing. Right? So if this number is always 0.148, or rather this KEQ is always the same by delta G, if P total goes up, right? So if we increase the pressure of this system, right, the total pressure of the system, by filling in more gas, that means that this part has to go down, right? Because this number is fixed. KQ is fixed by the energy difference of the two molecules, right? This number is not changing at constant temperature. So this is fixed. So as pressure increases in this system, this number goes down. What does this number measure? Well, this number measures basically how many products you form. Right? So as pressure goes up, this reaction becomes increasingly more and more reactant favored. Let me write that down. Right, this is a really interesting point. You don't really quite get this from ice, in my opinion. Is that we have a fixed relationship. Right? K is fixed to this number. Right? But K my screen is starting to come on. Oh, and there goes my crash. God damn it. All right, let me just rewrite this real quick. I am not having good luck today. We're almost done anyway. Okay. One more. All right, so we have KEQ is equal to 4n squared over 1 minus n squared P total. And this is equal to e to the minus delta G of the reaction RT. Right? So at fixed temperature, KEQ is fixed. So the amount of dissociation that we get, right, this is proportional to how many molecules of NO2 we form, changes as a function of total pressure. Right? So as pressure goes up, this association goes down. And as pressure goes down, this association goes up. So in fact, what this tells us is that, in fact, the real equilibrium behavior is not that it's not necessarily product favored. System is reactant favored at 1 atm, but NEQ increases as 1 over P total. Come on, start working. It's going to crash again. All right, I think that's my cue to stop. Right, so the idea again, right, so equilibrium, right, energy only tells you so much. But we have to consider the physical effects of the environment as well as the chemical equilibrium, right? And so we've seen a situation now where even though it says it's reactant favored, we can make it product favored by lowering the total pressure, okay? So next class we're going to look at a different example where the opposite is true, where you have a system that's product favored that doesn't want to form products in the gas phase, and we're going to make it form products, and we're going to change the world doing it.
Do you think you could explain that last part at the beginning of next class?
Yes, absolutely.
Thank you.
Yeah, I apologize.
No, it's okay.
I was just going to ask you, can you repeat what that last sentence was? System is
Yes.
reactant favored at 1 atm, but NEQ increases as 1
Yes.
over...
Let me just write it on the board.
I just want to have it in my notes. Perfect. I'm doing great.
On the railroad though.
So I figured out what happened
What?
I lost track of my thoughts because I swapped the two numbers.
All right, so K is fixed at fixed T.
When would I have lost this?
Right? Agree with that? Right? So
Literally every class time
as P total increases, as we pressurize the system, that means therefore that N has to decrease. Right? And vice versa. They have an inverse relationship. So this reaction at high pressure N is small, which means mostly product or mostly reactants. But at low pressure, the opposite is true.
High end mostly product.
Yeah, N is large, and this is a product favored reaction. So we're going to have to consider the fact that energy doesn't necessarily tell you everything about products, but also the conditions of the box, which is the pressure. And we're going to see that next class in even more detail.
Thank you so much.
You're welcome. Sorry about the crashes.
Not your fault.
It is because